Another phenomenon from calculus that gets introduced to you here in pre-calculus is the notion of calculating the average rate of change in a function. What the average rate of change actually measures is the ratio in the change in two y values between two given x values. It's essentially just a slope calculation between 2 points on a function's graph. So average rate of change in f of x, and remember that's going to be the function that you're analyzing, between two x values, x1 and x2. To calculate the slope, you need to take your x1 and x2 and then plug them into the function. So this generates the change in the two y values on the function, and here's the change in the two x values. It quite literally is the exact same thing as calculating slope. So when you're prompted to calculate the average rate of change in a function, you'll be given the function's formula as well as two x values to calculate the change between. So what you need to finish the calculation is to actually get the y values that pair with these x's. So I need to do f of x1, which is going to be f of 1. And remember, here's your formula. The function is defined as 4 minus x cubed. So an x input of 1 would generate a y output of 4 minus 1 cubed, which is 4 minus 1, which is 3. So that's essentially a point on the graph at x equals 1 and y equals 3, nothing more than a point on the graph. You need to get the f output value at x2 as well, which is f of 3. And again, go back to your formula. You're taking an input of 3 and you want to generate the y output. So 4 minus 3 to the third is 4 minus 27, which equals negative 23. So that generates another point on the graph of the function. X equals 3, y equals negative 23. So you don't really need to commit this complicated formula to memory. All you need to remember is the function tells you the y values that pair with your x's, and average rate of change is nothing more than the measure of the slope between the change in y over the change in x's. So it's best to just go ahead and turn those function input outputs into coordinates and calculate your slope. So your average rate of change, which again is simply slope, is just the difference in your y values, negative 23 minus 3, divided by 3 minus 1, change in y over the corresponding change in x. So you get negative 26 divided by 2. You have an average rate of change of negative 13. Now, a picture of what this number stands for after calculating the average rate of change. The function f of x equals 4 minus x cubed looks something like this. Let me do a makeshift graph of it real quickly here. It's a cubic function, has a y-intercept at 4, and looks, this is probably a little exaggerated version of the graph, but looks something like this. Okay. The 2 points we analyzed occurred at x equals 1 and x equals 3. Well, x equals 1 gives you a y output of 3. So let's say that point is roughly about right there. And the other point we analyzed was at x equals 3, which gives you a y output of negative 23. So that's most likely going to be way down here somewhere. So what this average rate of change actually measures is if you were to connect these 2 points with a straight line, then the slope between these 2 points, the change in y over the change in x, measures that negative 13 slope. Well, according to our calculation, you go 26 units down, going from this point to this one, and then you go 2 points to the right. So that's where we got the slope of negative 26 change in y over positive 2 change in run to get a negative 13 slope between those 2 points in the graph. Now, and that's what average rate of change measures, is just the average slope between those 2 points. So since we got a negative slope, without the picture, you can kind of take for granted a negative slope means as x goes from 1 to 3, the values of y are going down. You should be on a downward sloping portion of the graph. And the graph is decreasing there. And since you got a negative slope, that kind of matches up and syncs up with the picture that you have between those 2 points that you're analyzing the average rate of change through. Okay. Calculating average rate of change can also be applied when you just have the graph of a function and no formula. But it's the same idea. You're asked to calculate the average or estimate the average rate of change between x1 equals -3, so -3 right here, and x2 equals +3, 1, 2, 3 right there. Okay, so you still want to generate a couple of points. You still need to get the actual points, the two-dimensional points to calculate your slope for. Well, since you've got a graph and you know the x values, you need to know the f outputs. I need to know f of -3, and I get that information directly from the graph, just like we did previously. X equals -3 gives me a y output right here of +6. So f of -3 equals 6, which means that's the point -3, 6 on the function's graph. -3x, +6 for y. We need to get the f output at x equals +3. That's the other x value that we're analyzing in our average rate of change. So at x equals 3, you get a y value of, it looks like you're only at 2. So that's the coordinate 3, 2 on the graph, meaning that will be the other point that we'll calculate our slope through. So our average rate of change here, again, nothing more than slope, is just going to be change in y values. You go from a 6 down to a 2, so 6 minus 2 divided by the corresponding change in x values, -3 minus 3. Keep in mind, you had to be consistent with your order of subtraction. I did 6 minus 2 up top. I've got to do -3 minus 3 in the bottom to be consistent and get the correct sign for your slope. So that gives me a +4 rise over a -6 run, even though it sort of looks contradictory here. But that gives me a -2/3 average rate of change between those 2 points. And that seems to sync up with the picture. Going from this point to this one, if you connect them with a straight line, the average rate of change, or the average slope between those 2 points, is a -2/3 slope. Now, yeah, the function is actually decreasing, and then it increases a little bit on that interval, but since you get a negative slope, that means you have a lot more decreasing behavior than you have increasing behavior, because a negative slope is indicative of either all decreasing behavior, like on this first example, or, like in this case, just means you have more decreasing behavior than you have increasing behavior. Okay? So whenever you're prompted for average rate of change, it is perfectly healthy to make it synonymous with calculating slope.